This is Team 71, and today we're going to be presenting our design for the Mars Cargo Mobility System.
So I want to initially just explain to you how we approach the problem. So after we received the request for a proposal, we formulated this statement of what we needed to do. A macro rover needs to be developed that is able to autonomously transport 3 different types of cargo from the landing site to 3 different delivery locations at the miter. And this problem statement sort of guided us throughout the project. And sort of to explain what we needed to do, the whole purpose of this project is to create a macro so that when we eventually establish long-term stay on Mars, we do not need to risk the lives of the astronaut to retrieve cargo from different sites on Mars. And that is why we created this macro. So to explain what this means, we had this map that was given to us a couple of days before the presentation, before the demonstration, and what it shows is what we needed to do. So we start here at the landing zone, and then we go, and throughout the process, we face multiple obstacles, such as this obstacle, this hill, this cliff, and multiple branches throughout the course. And we need to take the cargo from the landing zone and deliver it to one of these 3 landing sites. To do this, our 2 main resources was the Lego Mindstorm kit, which was sort of the building blocks of the project. It was what we had: the light sensor, ultrasonic sensor, line finding sensor, magnetic sensor, and so many other different building tools in it. And then there was the Raspberry Pi, which was the brains of the macro, and it was what we programmed to do all the tasks we needed to do.
The main goals for this rover were to be able to follow solid, dotted, and dashed lines, to be able to scale obstacles, to read magnet sensors to indicate turning and cargo placement, and to be able to dispense cargo in the upright position. These goals were outlined in a more detailed fashion in this need-finding chart as customer needs, and were outlined as technical requirements and target values that we aimed for when we were designing the macro rover.
So in regards to the project management aspect of the project, we felt that we were very well organized throughout the project, and that allowed us to deliver things efficiently and in a timely manner. So when we first received the information about the project, we immediately created a work breakdown structure that highlighted everything from the request for proposal. We read the request for proposal very thoroughly, multiple times, and separated everything into first-level components, second-level components, and even with the prototype section, we had third-level components. We then took everything in the work breakdown structure and we created a Gantt chart out of it with dates starting all the way from when we began the project on the 3rd of October until the presentation day on the 17th of October. And this helped us constantly track our progress throughout the project so that we don't slip up and fall back. And then what I would argue was the most important part of our project management was our meetings. We had regular meetings at least twice a week, towards the latter end of the project, even 3 times a week, where before every meeting, we had a meeting coordinator who planned out everything we would do throughout that meeting. And that meeting coordinator alternated between all 4 of us. So it wasn't one person handling all of the load. And then throughout the meeting, we would we had an agenda that the meeting coordinator would plan. We would record our meeting notes, and then we would create action items for the next meeting. And we separated those tasks amongst the 4 of us. And this was very helpful in tracking our progress. And now when we look back, we can clearly lay out every single thing we did throughout the project.
We can begin our discussion of design philosophy by taking a look at the hardware of the macro and what the steps that led up to the final design. Our team began by creating 4 independent prototypes with each team member to allow for creative ideas to be explored, and different aspects of these unique designs were culminated into a morphological chart. This morphological chart compared the different methods that each team member curated with the functions that were required for the macro to achieve. We had visual representations of the methods that were being implemented to allow for a better understanding of how they could be used in the macro rover. The best aspects in this morphological chart ultimately culminated into the initial prototype. Some aspects of the design that had greater debate within the group were analyzed using decision matrices. The first time we made a decision matrix for the wheels, we decided that treads with 2 bigger wheels in the back was the best design, determined by its ability to be constructed easily, its turning ability, its stability, the requirement for motors, and the ability to move with efficient speed. In this first decision matrix, we were unable to consider the fact that the treads did not fit the wheels correctly given in the kits, and then this led to unstable performance. Adjusting for stability, we found that a 6-wheel design was the best to be used in the macro rover, and we adjusted this for our second prototype. Other aspects of the design were also analyzed in decision matrices, such as the loading pad, where the trailer design was decided to be the best, and the drop-off method, where we decided on using a gear pushing method. All of these different aspects were culminated into our initial prototype. This initial prototype consisted of a body that held the Raspberry Pi with one set of treaded wheels with 2 wheels and treads wrapped around on the main body. There were 2 larger wheels in the back that were attached to the trailer as well. This trailer consisted of a loading pad that held the cargo, a pushing mechanism that pushed the cargo through swinging doors that were attached with a rubber band hinge. This trailer was attached with a ball and socket joint to the main body, and ultrasonic and light sensors were placed at the front with a magnet sensor on the underside of the main body. As mentioned prior, this first prototype was adjusted as the treaded wheels were ineffective in its performance, and we found that the design in general was too low to the ground, allowing for no space to put the sensors, and it was too wide to be performing well on the track. This led us to move to a 6-wheel prototype where the motors were adjusted at this different angle to allow for more sensor placement room. And we had 6 wheels which allowed for the macro to move with more consistency. This design, though, in the main body had an uneven distribution of weight, and the greater friction forces on the back 2 sets of wheels prevented this design from turning. To take a creative approach to allowing the macro to turn, our team tried a design with 1 set of wheels in the front and 1 wheel centered in the back for 3 wheels on the main body. This design, though, was ineffective in turning, and we kind of took we backtracked to see what the prior design was lacking to cause it to not be able to turn. Ultimately, we went to a design that had 2 sets of wheels on the main body and 1 set of wheels on the trailer, with a total of 6 wheels, but by removing the tires on the back 2 sets of wheels, we found that the macro was then able to turn with the reduced friction forces. So this was all of those turning issues, and we also had a custom Pi case with the battery pack and the Pi stacked on top of each other towards the front end of the robot to create a different distribution of weight that allowed for turning to be more effective as well. We ultimately found, though, that this middle set of wheels prevented the macro from being able to scale hills, and this was adjusted for the final prototype, as Jonah will explain later. This trailer was ultimately attached using a permanent attachment to the main body, and this middle set of wheels was removed to create the most effective design in prototype number 5, which is our final prototype.
Alrighty, next up we have our design philosophy for the software logic. Here's the first part of the flowchart of our code. Over here we initialize variables, and then we have different protocols depending on the initialized variables, which is to get changed depending on the sensor readings. That's all very nice. One of the things that we had to hard code in was our speed choice, and that took a lot of trial and error to find a good speed that would allow us to complete the speed test well and also be different on the track so that it could go over obstacles and the hill. Here's more code. This is mostly the turning method. We have 3 different directions. So if it turns right and doesn't see anything and then turns left and doesn't see anything, it will go forward in the case of a dotted or dashed line or a break in the track. We also have 2 end conditions. One is user controlled, but one is completely autonomous. Our autonomous is if it goes forward for a certain amount of time and it still doesn't see any lines. One of the things I want to talk about is our recursive turning, because originally we did not use recursive turning. We just had the macro turn all the way to the right or the left and then check for a line, but we then realized that it wasn't able to read if it should have started moving forward between 0 and 90 degrees. So as our solution, we set up a recursive turning method, and we took a lot of time optimizing that to get our speed and wait time correct in between each iteration. And then another thing we had is our IMU as the magnet detector. Originally, we had the Hall magnet detector, but it was having a lot more trouble with reading the magnets than the IMU was. And so we switched to the IMU, which read the magnets a lot better, but that did mean we had to switch our code for magnet and cargo drop from digital to analog, which took a lot more research.
Okay, so now I'm going to walk through the interesting aspects of our fifth and final prototype. So this prototype had a length of 47 centimeters, which proved not to be very beneficial to us in terms of turning, as when this macro would pivot around, the trailer would slam into various hazards and objects, such as the cliff. The macro also had a height of 17 centimeters and a width of 21 centimeters. This proved to be very beneficial in terms of stability and providing us enough room to place our line finding sensor and our magnet finding sensor. The way our macro turned is through the spinning of one wheel forward and another wheel backwards in the front of our macro. This would then allow the two wheels on the trailer without tires to skid around in either a clockwise or counterclockwise rotation, very much like a pivot. As you can see in our turn test, we had an average minimum turning radius of 6.5 centimeters in the clockwise direction and 10.5 centimeters in the counterclockwise direction. This is pretty good. This is pretty low, although you may notice that there's quite a big margin of 4 centimeters between these two. And we found the reason for this to be an imbalance in the weight distribution at the front of our macro. There was more weight on the right side of our macro than on the left. And this is because of the placement of our homemade pie kit right here. And there was really no avoiding this due to the symmetry of the body and the kit, and also the alignment of the Lego pieces. The way our macro was able to drop off cargo was through the movement of this wall powered by a motor with gears pushing the cargo through this platform, through these trap doors held on by rubber bands. The cargo would then fall to the ground and the macro would drive off. As you can see in our drop-off test, we found that when the macro read the magnet and waited 1.6 seconds and then started to drop off the cargo, we were able to get a minimum radius of less than 1 centimeter. That's pretty good. Another interesting part of our macro is the weight distribution from a side view. As you can see, a lot of the weight is in the front from our homemade pie case here above the motors. There's also a lot of weight in the back due to this motor. And because of this, there's not a lot of weight in the center. And that created a lot of compression and depressions when the macro would accelerate and then stop if it came across a hazard with its ultrasonic sensor or lost the line with its line finding sensor. And this compressing and decompressing, much like the movement of an inchworm, would cause instability with little Lego pieces. Things would pop off like this little adapter, and maybe even a motor would pop off. So in order to ensure that our cargo was in safe hands and that nothing would fall out that was in great importance to us, we performed a trailer stability test by tilting the trailer as far as it can go until the cargo falls out. And as you can see here in our results, that the maximum tilt angle in the clockwise and counterclockwise direction is above 60 degrees. That's pretty good. There's really no hazard or obstacle that will cause the trailer to tilt that much in the demo. Another really beneficial and interesting piece of our macro is its ability to climb up inclines. We created this mock test of a macro driving up a binder, and with its great traction in the front wheels, with its front wheel drive and the rubber bands over the wheels, the macro is able to climb up inclines no greater than 35 degrees.
All right, lastly, we have our conclusion and areas of improvement. Our conclusions, it was a success in 2 of the 5 tests. We succeeded in the obstacle portion of the test and the speed test. We failed at the parts of the track that include the cargo drop, the navigating a dotted line, and the turn hill turn. But these things could have easily be fixed with some improvements to our design. Firstly, the build, our macro was very long at 47 centimeters, so we needed a shorter length because whenever it would try to turn during the navigating a dotted line or the hill turn, when it was trying to get on the hill, it would run into the cliff and it would be unable to complete its turns, so we would have to adjust the length for that to be able to work. We also had some issues with our cargo drop doors. They are held together with rubber bands, and the rubber bands in earlier times were too tight to let the big cylinder or the cube go, but they are currently too loose to let the cone go. We also had some issues with our code. The turning code for navigating was a bit less efficient than we liked, and we believe we could have optimized that more by adjusting our counter variable and the wait time. Also, our magnet code didn't turn out as we planned. Our IMU sensor did not sense the first magnet it ran to, even though it would sense the second or third. Also, the IMU code stopped working entirely partway through the demo, and it was unable to run the code without commenting out that portion. So yes, thank you for listening. This was the Team 71 macro.